this is the SIG Auth meeting from December 14th. We have two things already on the agenda. One is discussing the service serving cert signer that exists in OpenShift. As far as recording goes, I'm reasonably sure that this records the entire meeting, everyone who speaks, not just me. Then the other thing on the agenda is the Vault controller bit. Eric Toon coordinated that. I don't see him here. I'm going to go ahead and move it out of the agenda until he's able to work it out, because I don't see Kelsey here this time either. So the service serving cert signer. Let me see if I can share just a piece that I want. The service serving cert signer is a piece from OpenShift, which you can annotate a service, and then you are able. Why are none of these labeled? And that broke. Well, clearly I am not as skilled as Jordan.
Are you trying to share your screen?
Yeah, I'm trying to share the one application that I want, and none of the Chrome ones are labeled. All right. Well, none of these are pornographic, but there are some code reviews on it. What are you guys seeing right now?
I'm seeing your screen. I'm seeing the meeting notes.
There we go. That's exactly what I wanted. Good. All right. Is there a bunch of code reviews on the screen too, or hopefully those are excluded?
You're being really, no, yeah, there's not. I was gonna make a joke, but
okay. Like, ooh, that's gross. Okay. So they allow you to. One of the problems that you have today when you create your service, if you wish to secure it, you have no easy way to create a serving certificate for yourself. You can't sign for an IP, and really nothing is ever going to be able to sign for an IP because the IPs for services can be reused. You need to be able to sign for an in-cluster DNS name that you can use to answer requests so that when someone relies upon your service, they can confirm that they are talking to you. It's important that you end up with a serving cert that can be trusted. So it has to be signed by someone in authority, and an individual author is not going to be trusted with those keys. You could go through a certificate signing request process where you actually create your certificate, you send it off to be signed, you get the signed version back, you use that, you embed it inside of your namespace, you use it, mount it inside of your pod, and you run that. That procedure works, but if the platform itself owns DNS and the platform itself controls traffic routing, then if the platform can also inject a trust certificate for you and a serving certificate that it has signed that only you can use and get traffic routed to you for it, it removes all that complexity for you. You create your service, you annotate the service saying, please create me a certificate, and then your template makes use of it. And let me find the example that I had of actually doing this in OpenShift. It is as easy as annotating your service, and then the pod that you create simply depends upon the secret. And because of the way scheduling works, your pod won't be scheduled until the secret exists. And so you get launched, and you are able to serve with your serving cert, and then we inject the trust certificate into the service account secret that gets automatically mounted. So I can pause here and see if that's clear how it works so far, and if someone has concerns about exactly what is getting signed.
I mean, that sounds pretty reasonable, particularly since, yeah, I seem to, so it's just adding another secret to the service account that happens to be a server certificate plus maybe another CA that establishes trust with other things signed by that
Right.
certificate chain. And then it's just at a well-known location so you can grab it. Is that a summary of the?
It is. And are you guys able to see this screen? I gotta be able to see what you're seeing. This is crazy. Do you see the OpenShift repo and then me searching for a file?
Yeah.
Yes.
Excellent. So the piece that actually makes this work in OpenShift is, oh, that was the wrong one. Is right, bigger font, is right here. So what this does right here is it creates a deployment config is roughly analogous to a deployment for Nginx. It creates a service for Nginx on the exposed line. It annotates that service with the annotation that says, make me a service serving cert. Then it mounts the volume and attaches it to the deployment. And then it says, hey, actually use that. That's what this config map does. And then it waits until it actually runs. And then once it runs, that means that the secret got created. And then we can actually test from within where we are a curl. And somewhere in the script it actually proves that it works. But this step right here is all you have to do to be able to get your serving cert. And it is an extremely powerful and useful feature. There are a couple pieces which, and I guess I can actually pull those lines out and put them in a note somewhere. There are a couple pieces that I think are unique to OpenShift and the OpenShift router that make it easier to do in a way that aren't the same in Kubernetes. So one thing that we have with our router is we have a re-encrypt mode for the router. So SSL terminates once at the router, and then from there, the router will re-encrypt and make the connection to your service separately. My understanding in Kubernetes is that an ingress actually opens you up and your service is directly exposed. There's no layer in which you can actually do the re-encrypt piece. If there's someone who's familiar with the networking, that would be great to confirm. Who else? I can no longer see what's in the meeting. Who else? Does anyone else here know for sure?
I don't know for sure, but I believe that that ingress controllers only do TLS termination right now. They do not. That it is possibly on the roadmap to do
right
encryption, but it is not a feature today. I think you can do. I believe you can do with ingress, like lower layer forwarding, but
okay,
quite sure.
That matches my understanding as well. So in OpenShift, that allows for a complete end-to-end flow. In Kubernetes, I am not as sure. The only other unusual piece is that bit where we change the service account token secret, And changing that service account token secret is unusual, but I think that if we wanted to do it inside of Kubernetes, we would be able to. It will have interactions with people's preferences about auto-mounting or not auto-mounting, right? You end up like, I want to auto-mount public but not private information. All right, so I guess at some later date, or I guess now, if somebody wants to say, hey, that's a thing that I really want, we could see about at least making a feature for it and then deciding what we want to do about it. I'm not attached to the idea. It is an external controller, and as we get more and more external functionality working through the API machinery pieces, it'll be easier to integrate. So I would.
So for clients, I see that you distribute to every pod the, I guess, self-signed root CA cert so that they can have a chain of trust. But how do you tell clients to not look in the normal browser cert, but to look at wherever you put this self-signed thing, or to also look there, because they also need to crawl the internet, then they need to have two places to look for stuff.
Inside a pod, the pod will have to make the choice for the individual request that it's making. The presumption is that the pod actually knows, am I calling a service or am I calling something external? And if it doesn't, it can say, do I trust this or do I trust that?
So you can't use this without changing the source code of clients. You can't like drop in a third-party thing, program that wants to talk to a database and then have with TLS or I don't know, whatever.
Well, being able to trust a different CA bundle isn't unusual. A cluster admin could also make the choice and say, we recommend you start from this particular base image when you build your containers on top, and that base image includes the CA. I was not prepared when we created this feature to say that this should be injected in the system trusted certificates for all containers without their permission.
Had anyone looked at like actually using a non-self-signed chain to generate these, maybe with like a name restriction or something?
Oh, I wasn't actually aware that clients would conditionally respect a certificate based on who had signed it, or based, yeah.
I just meant like, couldn't you go to a real CA and then get a cert that allows your organization to generate more certs and then use that sort of intermediate one to generate these, and then clients that use normally installed browser certs would find a chain of trust leading to a well-known CA?
We will accept any signer you want to give us. If you give a different signing key, that would work fine. It was a level of comfort with having a by default trusted key visible externally, even though we anticipate essentially every use being internal, right? We saw this as I communicate from service to service using this, but by the time I terminate at a client, I am being served by a route, and the route that serves me is signed with a truly official CA, right? So I signed ebay.com with my official cert, and it happens to come in, go through a re-encrypt bit because I don't want my pod to have that particular certificate available to it in case my pod gets compromised or something goes wrong in that namespace. And so when you get down to that level, we have a almost throwaway signing key.
Yeah, I was going to say, this seems like a very different feature than Ingress. that it would be something internal to the cluster, not that you would be exposing these CAs to the service to the internet.
And that was why we only signed for internal names. We can guarantee on the platform that if we sign for only internal keys that should only be routable inside of the cluster from one pod to another, that we have signed for something valid and that no one can reuse it, right? If Eric steals David's signed certificate and key pair, but he's in a different project, Eric would have to own DNS or traffic routing to be able to use that particular cert key pair.
I mean, this seems like a very good, this seems like a really good base level thing, or low level thing to have within the cluster. I'm wondering, in terms of feature, my primary use for something like this would be basically for ingress to allow that re-encryption. I don't know if that's just me or if you guys use it internally for communications between services.
There are inter-service use cases now, right? As we add extension API servers or third-party API servers that don't ship with Kubernetes, the work done in API machinery to allow that presupposes that you are going to be running these additional API servers inside the cluster. They are going to have to be backed by some kind of storage. There is benefit to saying that the storage is etcd, but it is an etcd that is in your namespace. It's not an etcd that you're sharing with something else, so that you can't have an extension API server that is dominating rights to your core etcd. And in those cases, you end up wanting to have serving certificates for etcd and trust inside of the API server that then calls out. I hit it just last week. So there would be some utility there.
Yeah, and we've also just seen that a vast majority of the applications that people write use HTTP internally.
That hurts me. What I realized when I was working on that extension API server for the API machinery work was that if you do that, there's no way, at least that I saw, for etcd to confirm who is speaking to it, because it's in the clear. And so anyone is then able to read the data directly from my etcd if they have access to the server.
Yeah.
And it takes extra work for me to make sure that doesn't happen with something like network ingress policy.
Yeah.
Which, obviously is concerning.
Yeah.
But this would be a clean layer on top. I could see developing it separately as an incubator project if we wanted to. I don't have time at 1.6, but I could see it in 1.7 or 1.8. Sometime in 2017, if we wanted to do this, it would be possible.
Yeah, it's hard for me to say because I don't have enough expertise on basically public key infrastructures to say that this is the absolute correct way of doing it. I definitely see the value in trying to encrypt more traffic inside the cluster, but I don't know if I personally can endorse it as one way that we should go.
Sure. This has been recorded for posterity. I'm sure someone will let me know.
Yeah, perfect.
Hopefully politely, not with a, hey, guess we can do an OpenShift.
I know this sounds pretty cool for us. I mean, I deal with healthcare and patient data a lot. So for us, everything has to be, TLS inside the cluster and out.
Mm-hmm.
And, a lot of times we just generate self-signed certs all over the place to ensure that encryption layer. But
yeah,
so it sounds helpful to help, speed us up with that, because we have, a million self-signed certs sitting around in different places. And usually we throwing them in with secrets. So, if it's already there, that's kind of cool.
Great. There is the one challenge that came up when we were doing it is that we didn't have a do this to get around is the health check, right? So part of what happens, and Eric Toon brought this up before, you have to regenerate these certificates, right? So if you're regenerating the certificates, I don't know, a couple times a week, what happens is your pod is going to be running for a longer period of time than that. And the pod has to get that new secret. Paul Morey solved that for us, someone on that team, a while back. Secrets get updated in place now, but most applications read their certificates once, and they do not read them a second time. And that means that you end up trying to do unusual things inside of your health check, right? The simplest way to get yourself kicked and have your process restarted is to fail health check and then see a little kicky for you, right? So a health check that can go through and say, I am serving with a certificate that is not current. And if that happens, I have a 1 in 100 chance of saying, I'm unhealthy, kill me. Means that you are unlikely to bring down all of your pods at the same time, because that also has negative repercussions. But one pod at a time will shoot itself in the head and restart, and it picks up the new certificate. I think that would be a problem that I would want to solve before we took it too far.
Jordan brought up a couple meetings ago, the fact that we...
Sorry to interrupt. Kelsey's here, but he has limited time. Could he do the demo, and then we could loop back for more questions on this after?
Sure.
Is that right?
Sure,
We're lucky to have him here. All right. Kelsey, thanks for coming. Can you switch to your demo?
Yep. So yeah, sorry to interrupt. It sounds like a good conversation was kicking off there. And I think my demo is kind of in the same vein. And I'm just going to kind of show a prototype that has been working for some customers already, but we can do much better. So this is really more of to show the prototype, kick off the ideas, and open it up for discussion. So I'm going to share my screen. Can I share my entire desktop? Screen. All right. So I'm taking you guys can see my screen, this GitHub page here.
Yep.
All right, great. So I'm just going to show this Vault controller. There's a couple of parts to it. I'm doing this without modifying Kubernetes. So there are much better ways of doing this, but the goal here was to give something people could try in any cluster without modification, okay? So one of the things that a lot of people want or criticize Kubernetes for is not having real secrets. And I understand where I have empathy for them, right? They like Vault. They like the way Vault is marketed. They like the way it's pitched. And it seems to solve a problem when they don't necessarily have all the things you would find in a cloud provider, such as encryption at rest, those kind of things. So Vault is becoming a leading solution in the open source space, I would say. And it has a lot of mind share around being focused on secrets. So what some people want is for each pod instance, so not a shared key, but one per pod instantiation, to have its own unique token that's tied to the identity of the pod itself, right? So you can imagine you would have tons of these and they need to be garbage collected, which would be handled by something like Vault. Once you have one of these unique tokens, one thing people like about Vault is the ability to do dynamic secrets. So Vault has all of these backends, PKI, MySQL, Postgres, even Amazon IAM roles, right? So if you want, you can actually read from a path and a dynamic secret will be generated for you and it will have a short TTL which will expire or can be renewed, right? So maybe most of you know how Vault works, but that's a high level description. So the way this works is we need a way to give each pod a token at runtime. Now, one way would be to use an emission controller and kind of rewrite the pod to inject a volume or secret at runtime, but that requires modifications today in Kubernetes, so we can't do that. The other way would be to have the kubelet do it, right? The kubelet could look at a new secret type, new volume type, do this whole flow and inject the pod and keep the token renewed. Again, a few modifications required there. So the workaround is to use an init container. Init container knocks on the door of the Vault controller. The Vault controller can't trust this particular pod. We don't know if it's a real pod or not. So what we do is go to the Kubernetes API and we look up a pod with that name. If we find a pod with that name, we also look for a few annotations, Vault Project IO policies. And given that, we will then create a token, what we call a wrap token in the Vault world. So it can only be unwrapped once for its target, and then the real token will be underneath there. If someone beats you to the unwrapping process, you can raise an alarm to know that that man in the middle has taken your token. And we will then write back to the pod. So we get the pod IP from Kubernetes, and we write back to the pod init container. So the init container is up and running. It's listening on a well-known port, and we give it the wrapped token. The init container's job is to unwrap the token by talking to Vault in step 5. And in step 6, the init container can write the token to a shared path, a shared volume, and that will allow the container to come up and read the token to grab further secrets, right? So what I'm going to do is kind of just show this in action, and then I'm going to show you. Yep.
I actually have a question at this point, right? Step 1 in the flow that you described. What keeps me from lying about who I am?
You can lie all you want. You can say that you're pod foobar. You can lie. You can do whatever you want. You can be malicious. And all we're going to do is go to the Kubernetes API anyway, disregard who you said we're going to take kind of this advisory name that you've given us. If we find that pod by name in the Kubernetes API, we have to trust the Kubernetes API. No way around it. If you're in the Kubernetes API as a real pod manifest with the right annotations, we are assuming that the administrator had the credentials to create that pod with those annotations, and therefore you should get a token.
Okay, and I assume that step 4 uses the pod IP that it retrieved from the Kubernetes API. It does not trust the connection that was made to it in step 1.
That's exactly right. And the code is here on GitHub to verify that. So I actually get all the information for subsequent calls between the controller and the pod from the data in Kubernetes only.
Okay, so for me to intercept it, I would have to know a pod name, give you that fake pod name, and have control of the way traffic got routed in order to route myself that secret.
That's right.
Okay.
And once you do it, though, so the thing about this whole wrap token thing that the HashiCorp team has, they expect that use case. They expect you to man in the middle and unwrap the token. Once you unwrap the token, the man in the middle at step 4, step 5 will fail because the token has already been unwrapped, and Vault will raise an alarm and say, hey, this is trying to be unwrapped twice.
Well, presumably if you intercept step 4, you would delay the response so that no one could raise an alarm until after you'd already used it.
It doesn't matter. If you wait too long and step 5 beats you, then when you go to unwrap step 4, the thing you have is garbage. The real token is behind the wrap token in Vault. So only Vault can respond with the actual token that you need to use going forward. So this is a one-time use token that we're passing on step 4.
But a man in the middle can intercept the wrap token and then use it to unwrap. But no. If in a race condition situation, absolutely.
Yes.
But it's detectable. That's yes. The key, right? If the real application doesn't get the token because the wrapper has already been used, then that'll raise a red flag, and you should be able to use the audit log to find out what happened.
That's right. That's the goal of this. It's not to prevent, but it's at least to be able to identify quickly that it happened.
Okay.
All right. Good question, by the way. So now I'm just going to walk you guys really quickly through this. I have this tutorial online, so you can also follow through on any cluster OpenShift. It doesn't matter. So here I'm just going to download this controller or all this setup, and we're just going to deploy it really quick. I'm going to try to go really fast, not to waste your time. But I'm just going to create a new namespace here. So I'm going to pop over to my terminal. Everyone can see my terminal. Say yes.
Yes.
Good. Okay. So I have my terminal, and I'm just going to create a namespace so we don't junk up the place. Here, I'm just going to now deploy Vault in dev mode. So there are better ways of deploying Vault, but we're not going to waste time with that. I'm just going to say, hey, stand up in dev mode and use this root key so we can actually go on with this demo pretty fast. But it is a standard Vault container that I'm getting from the Docker Hub, managed by the HashiCorp team. So at this point, we should have Vault running inside of our cluster. So there we go. We have Vault. The next thing I'm going to do here is really quickly create a secret for Vault or our service. Now, this just tells us that we can now reach Vault over a standard DNS name, common Kubernetes stuff here. And this is the key that we've pre-populated with in dev mode, so that way we can easily start to manage this Vault cluster to configure it, okay? Now, the second part is, this is a custom component here, the Vault controller, a very small shim to execute that flow we saw earlier in the diagram. And we're just gonna create a secret for it so it can access Vault using the master secret. So it's going to, we could create a lower privilege token that can just do everything on behalf of pods. That's up to you, implementation detail, but Vault does have that where we can create tokens that have lower privilege than others. Now we're just going to deploy this controller, very simple controller here. All it wants is to know where Vault is and what token to use. And of course, we're just going to read that token from a secret and make sure that it's mounted as an environment variable. And we're just going to set a wrap TTL, so when we create wrap tokens on behalf of pods, it all works. So given that, we're just going to run the controller in the same namespace that will be able to talk to Vault. So now we have pretty much the core infrastructure in place. So now we're able to kind of use this new service in Kubernetes. Once this actually completes, kubeproxy and Vault itself are spinning up. So now we're good. Core infrastructure is in place now. Let's create a service for the Vault controller so pods know who to ask or knock on the door to get this request flow going. So now that we have that, we now have the 2 bits we need for Vault in this. Now, what I'm going to do now is skip to this use case of short-lived TTL certs with mutual auth between microservices. So talking to customers out in the field, everyone wants to do things with network policy. It all gets so complex. And an alternative would be, let's use short TTL certificates. In this case, in this demo, they only last for 1 minute. Of course, you can bump that higher if you want. But the goal here is that we will make explicit use of multiple PKI backends. So 1 CA per service if you want. That way clients have to get a specific client cert from 1 PKA to talk to one particular service. So that does mean that clients may have to have 20 different certs if you want to be that granular. But that is totally up to the implementer and person using the service. All right. So the first thing we need to do really quick is we're going to configure Vault really fast. You can kind of see what the developer workflow would be, or the system administrator. We're going to get a reverse tunnel to Vault running into my cluster since it's not exposed publicly. Now I'm going to hit Vault from the client. So I'm going to hit the Vault address, configure the token so my local client on my laptop can hit it. We're going to make sure Vault is running. So we see Vault is up and running. This is great. Now let's try to configure it really quick. So I'm going to go pretty fast. I'm going to mount the dynamic backend for PKI. You can mount as many PKI backends you want. Again, 1 for every microservice if you so choose. Once you have this PKI mounted, you need to configure it. So what I'm going to do with this series of commands here is we're going to configure the CA for time and a couple of other things. So here we're just generating the CA cert for cluster.local. Now, one thing to keep in mind, all of these certs and keys are available inside of Vault. There's an API for clients to grab anything that they need so that they can trust this client as well, or trust this particular CA.
Vault will not leak keys.
Right, it doesn't leak the private keys, but the cert keys are the public keys you should trust are there. All right, so now I'm just going to write a little bit more configuration for Vault. All right, so now we're getting close. So now at this point, we're going to do 2 policies, one specifically for clients only and one for servers only. And then we're going to allow these certs to be generated for cluster.local. And one thing that we're doing is we're making sure that when we do have the clients generate these certificates, they're generating them to be trusted by every possible communication mechanism. That includes the pod IP, localhost, service name, that namespace, that service.local, and also for the custom namespace that we grab from the pod metadata itself. And we'll see that in a bit in action.
Now, is this pod IP, you're fading out a little bit. The pod IP, are you interacting with Kubernetes in some way to make sure that that IP is not reused in the time frame where this cert is alive?
What we're doing is grabbing the IP address at the client based on what it's been configured with, right? So if there's conflicts on the same system or in different systems, I am not detecting that. So if you're issued the same IP, you're probably gonna have other issues, but you will then be able to have an IP address that's trusted by everything else. So we're trusting Kubernetes to allocate IPs.
Well, okay, but when Kubernetes allocates the IP, it'll allocate the IP, then I get a certificate signed for that IP, then I delete my pod and wait for somebody else to get the same pod. I take it you're just saying that the only way that I get to use that is if I gain control of networking routing?
Nope, let me show you. So this is a great question, and we'll show you what safeguards we put in place for this. So let's create this server role, client role, server role. So right, we need these two policies. So that way, so remember, everything is based on policy. So while you may be able to spoof the IP that you get your cert signed for, you won't be able to generate a certificate unless you're trusted and supposed to, okay? So here, we're going to write this policy. So this policy says, you can be a microservice and you will have the ability to grab a client cert or a server cert, but you need a token created with this policy set in order to do that. Not everyone can grab one of these certs. Let's push this policy to Vault really quick. All right, policies inside of Vault. Now we're ready to go. So at this point, you have these two paths. Now, how do you tell a pod what policies it's allowed, right? So we'll put this as a annotation in the pod. So this will let you, as the administrator, say that you get the default policy and microservice. The Vault controller will generate your token based on this policy. So even if you have a pod that has one IP and it were to go away and another pod comes up in its place with the same IP, then it needs to have the same policies in order to be able to get a certificate to be the same server or microservice that the other IP was servicing.
Kelsey, what's
the
the
client certificate that got signed? If I write a pod, the client certificate signed or whatever name, I extract that client certificate. I kill my pod, wait for another pod to be created with the same information. I now have a cert key pair that was signed for a pod IP that now belongs to somebody else.
Right, and here's the problem. It's so short-lived that, yeah, if you can convince Kubernetes to route you for that particular service, right, to that IP address, so you went in there and you got added to the service backend, you have all the same pod labels, but you don't have the annotations to get your own certificate, even if you get a Vault token, your token is not valid to renew that certificate you just stole, and it's going to expire from underneath you and become untrusted by everyone, in my case, in about 30 seconds.
Kelsey, what's to stop someone from just declaring any old policies they want?
Well, that's just the problem with Kubernetes. If you want to, you can create all the policies you want. So you can use RBAC. You know, when you get that pod definition in OffZ, you could say, no, you're not allowed to create a pod or replication set or deployment that uses these policies, right? That would have to be enforced higher up in the stack around just overall OffZ. What can people push? It's like referencing a secret. What's stopping someone from referencing a secret in Kubernetes by just putting a secret volume in place?
Well, don't those questions have to be answered? Like
well,
with code and technology and so forth?
Well, that's the Kubernetes model, right? So this is what the whole, a mission controller thing is about, right? If a specific user, you get a chance to inspect the object that they're trying to create. And if you don't want a specific class of users creating objects that have references to specific secrets, then your job at the OffZ layer would be to look at the request and deny it based on your company policy.
Is that now in Kubernetes? The
No,
ability
it's
to do this?
not. It could be built, but it doesn't exist today.
Right. So Kubernetes, from what I'm discussing right now, is a framework for doing these things. If OpenShift wanted to do this, OpenShift could provide a mission controller and a UI to let a user do this. Right. I've seen some startups with their own policy engines that do this today. They have these custom emission controllers. They compile the Kubernetes binaries, and now the user can now say, hey, use this emission controller.
Yeah, I'm a little concerned that we're not shipping a default implementation.
Well, that's a problem in general, right? So if you take away this whole meeting right now, you have that problem anyway. Just in general, Kubernetes shortcoming in terms of a framework. If you really want to see that, I definitely think we can probably create a whole issue around what the default implementation for Auth Z should look like at that granularity for an admission controller. But until then, most people are using Kubernetes, and what they do is lock down who can access and create these objects. So this is a solution for the current world that doesn't become invalidated if someone adds one of those admission controllers in the future.
Another thing I noticed is that you're using Vault in HTTP mode as opposed to HTTPS.
Demo.
Okay.
It's a demo. We want to make sure it's easy, because if you want to use, and I have a different repository that shows you how to run a production grade Vault, you need a CA first or certificate, so that way you can lock down Vault with HTTPS. Then you need to provide that particular secret to all the clouds so that they trust that particular endpoint. So that's for production deployments. But for this concept, this idea, this is enough to communicate the flow, but totally in production, lock down everything. All right. So, go ahead.
Quick question. So a lot of this sort of assumes that the client is vault aware, if I'm getting this right, in terms of like using the token to get a new cert and that kind of thing.
So this is where we decide what we want to do, right? We could either have a third-party resource where a user could say, you know, I want these kind of things for this class of apps, and we do it on behalf of the pod. The kubelet could assume this role, or the app itself can take this role. So today, a lot of people in the Vault community are just need a token that's unique, and they'll take care of this themselves. So you're right. This assumes that today the application would be aware. That could be an init container, it could be a sidecar container, it could be the kubelet, or it could be the app itself.
Yeah.
All right. So once we have this, we now can start using this annotation to start to do policy. And again, we're going to go with the administrator has the right to do this, and it's locked down, right? But this is a great observation. Now, what we want to do now is have our apps that are Vault aware. How do they request their certificates? And again, this is a feature that we could provide if we wanted a generic, you know, plumb the container with the well-known certificate that we renew ourselves with the kubelet. And in that case, what I'm doing, and I wrote this code so we can see what we would do in the kubelet. So here, we're going to get the pod IP, because since we know it. We'll also take localhost, because you could have an actor inside of the pod wanting to talk to the service over localhost, but over HTTPS. And then here's all the DNS names from our spec, right? So here's the possible ways that someone else external to the pod could communicate with the pod. So we need to make sure that when these certs are requested, the CSR includes all of this information. So we just do this, and I have code that shows how I'm forming that request before we send it over. But this is just something we need to do just to make sure people don't get in the habit of turning off verification because they ended up talking to the pod, maybe through a pet set declaration versus the normal service endpoint that they may use with the VIP, okay? So once we have those, let's just take a look at the server implementation. And I'm just going to show you guys the logs so you can kind of see what's happening here. And we're almost done. Thank you for your patience. Here, what we're doing is, this is kind of nasty, but it's all we have for now. We have this annotation here. So I want the default and microservice policy. I'm also giving you a hint at the TTL that I want. So no more than 24 hours is the max TTL for the token. And then here's the init container. So this is a little helper to kind of demonstrate the idea. So Vault init, its job is to go through that workflow we saw in the diagram. It's going to get its pod name from the downward API, the pod namespace also from the downward API. And then it's just going to ping, well, we need to talk to Vault on step 5 where we actually unwrap, but we also want to talk to the Vault controller. So here's all the data we need to make that initial request to start the flow. Now, this app will also listen on a well-known port on its pod IP, so that way when the callback happens, we're ready to go. And then we're going to write the resulting unwrapped token to this particular path, so just following a very similar pattern we do for service accounts. And you notice down here I have a shared volume with empty dir, just to ensure that when this pod is deleted, the secret is cleaned up. We share that volume out with whatever application will be running long-term after the init container completes, all right? So init container runs, it will execute, and then our pod takes over. And again, this is just client information. So when we go and generate our certificate, we need to know the pod IP, the pod name, and also we want to know our namespace as well, okay? And then we also need to know, and then I just have flags for that. So this is just code that shows what we could do in the kubelet if we wanted to. So let's launch this server really fast so we can actually see this in action. So the server code is being deployed. It's going through this init flow. I'm going to create a server, a service object for it so you can other pods can communicate. We'll look at the logs for it really quick. So I'm going to look at the logs for the Vault init container. Let's just do C. We just want to look at the Vault init container. So here you see the Vault init container tries to clean up to make sure the secret's not in place. It talks to the controller. We get an error because it's not, my IP is not there yet, which is okay. We try again. And then we get the wrap token from this Vault controller. We unwrap it, so we wait for the callback, and then we unwrap the token and exit. So this will allow the rest of the pod to continue forming. And once the rest of the pod goes, you can see what it's doing now. So it reads its secret from the Vault secret path that we created earlier. It looks at the TTL and knows that we need to renew it. So we know that the next renewal, so we do our first renewal, and then we know that the next renewal should be some algorithm, roughly half of the expiration time. And notice here that we're already obtained our cert, and we're going to renew it every 30 seconds roughly, right?
So this, Kelsey, this controller is dropping a new certificate and basically sharing it with the server or client, like via cross mount or something?
So,
bind mount?
So the Vault init container, its job is only to produce the token and drop it into a shared mount that we saw from this. And then once the mount is in place, right, once this shared volume, this volume here, once that's in place and the container starts, its job then going forward is to renew that token using the normal Vault APIs and generate its own certificate.
Okay, so only the wrap token is shared.
The wrap token isn't shared. So the wrap token is the only thing shared between the controller and in a container, correct?
Got it.
And then the pod is responsible for doing the unwrapping because it's the only thing that can know what's in the real token used by the pod.
So how would this handle generic secrets, right? Certificates are certainly one case. I can envision worlds where you have a token and you can use your token to access a key to be able to get a key to decode my database password or something. But in the general case of a token or a password or something inside of a secret, how does this help me?
Let's finish this use case and I'm going to show you. And I'll answer your thing. So we're going to finish this up really quick. So we have our server with a unique cert renewing in the background, doing the right thing. So if you hijack the cert, it's not going to be good because you won't be able to renew it. That's the whole point of these short-lived TTLs. So the next thing we want to do is start the client. Very similar code, except for it's going to request a client certificate using a different backend in Vault. And then you'll see a very similar thing that happens with the init controller, so we won't look at that. But once the init controller finishes, it's still initializing right now, we see that the cert itself, the client, grabs its own certificate and starts renewing it in the background. So now it has a certificate trusted by the server, and you can see it creating, successfully doing a TLS handshake and getting a response from the server that we trust, right? Everything is end-to-end validated, and now we kind of have this service. So if we auto-scale any of these things horizontally, everything will go through this flow, grab its own unique certificate, short-lived and trusted. You have this kind of real ring of trust using the Vault PKI, okay? So this is kind of the use case, and a lot of this functionality we could do transparently underneath the covers with the kubelet because we pretty much have most of the information that we need to do this kind of thing. So I guess before I wrap this, to the other point about these things renewing, these apps actually know how to deal with renewing things. So they understand that when I get a new certificate, how to serve it at runtime. Go makes that really easy. We can just replace the in-memory representation of the certificate, and the next TLS handshake will use the new cert to handle the next request. So that's pretty smooth. We don't really need to rely on much else. Now, the last question you had was about generic secrets. So
well, I mean, there are other things in the world besides Go, right? Like you have the same health check problem with your Java app as any automatic service signing piece, right? They aren't built to automatically pick up changes.
Yeah, so it depends, right? So I actually have this problem as well. And what I normally do in my apps, I actually listen to a kind of a trusted HTTP endpoint for health checks. So if you just want to ping me, I'm just going to respond 200 if I'm healthy or not. I tend to just rate limit that, but it's not HTTPS, and I may make it only internal to the cluster. So I expose 443, but I don't expose the HTTP endpoint, which gives you access to the routes that you're health checking.
Sorry, no, I meant that that when that certificate gets replaced, it's easy in Go. People still don't do it very often. Kubelet.
You're right. Yeah, a lot of people.
It doesn't happen in Java. You still have to handle a way to how do I kick something? Either everything in the world gets updated to be aware. We haven't gotten there yet, or what?
Yeah, I mean, you're right. I mean, a lot of people want to do the thing where they have a bunch of administrators that go around restarting services to pick up configs. And that issue, I definitely think, someone has to solve, not me. I tell people, look, you want to take advantage of this cloud native world, then you need to be able to do things dynamically. And if you don't want to write code, great, find someone to solve the problem for you. So I'm with you. I have empathy, but I just can't spend a bunch of time on behavior, right? This is a human behavior problem. I don't want to write more code. Great. Have fun with the pain. So fast forwarding past that, I get you. But, these are solutions for people. If they do want to exercise at all, we have it available.
So the OpenShift proposal earlier, or not the proposal necessarily, but just the conversation about how OpenShift does some of this, it still sort of has to deal with the idea that certs will expire, and applications won't know how to update them. In the same way, we have had discussions in the past about service accounts and trying to do rotation around service account credentials beyond just tokens. And I think that a lot of those conversations, and including the Vault thing, sort of go into how do we rotate secrets when the applications aren't aware. So that seems like a general theme rather than.
Yeah, at Zendesk we've been talking about the ambassador pattern a lot, where we delegate those issues to a reverse proxy that basically decorates the request with authentication information, so the application doesn't have to be aware of it. And then the decorator or ambassador app is then responsible for working with Vault to rotate credentials.
That's actually a forward proxy you're talking about, right?
Well, it's a reverse proxy because the app doesn't. The app thinks it's talking to the reason it's called a reverse proxy is because the application doesn't know that it's not using a proxy protocol, which is like when we think of forward proxy, I'm thinking of the old traditional SQUID, where basically you're requesting a resource on behalf of another resource explicitly. But for the reverse proxy, you're talking to the ambassador as though we're the foreign server. And
you probably have ambassadors both on the client and the server side to just like manage the connection.
You certainly could do it that way. If you didn't want the server to be, if you wanted them to move in lockstep and you didn't want to put special code in the server to do it, you could totally do it on both ends.
Yes, I think this is
complementary to that pattern.
Yes, I think this is like, all right, once you have this kind of mechanism in place, you got choices. You can just take the token, go to town yourself, or we could do more help for the user and say, hey, we're going to plumb a well-known location with things like, key value pair secrets and certificates, and your choice, you can consume them in your app, we'll renew. Or if you don't want to consume in your app and you don't want to provide like a hook, maybe you will handle a specific signal that we can send to any generic app. You handle the signal which tells you to reload configs or certs. Or you're right, we could decide that we have these sidecars, but in the pod world, that's just kind of the user's choice, right? How much do they want the platform to do for them?
Yeah, but I think we need to meet the world where it is. right?
And also, like a lot of app developers are really constrained. Especially if you're moving legacy or sunsetted apps into Kubernetes. Having ambassadors may be your only practical option.
Right, but the ambassador itself would work the same way as a developer that did decide to actually consume those secrets, right? And be responsible for refreshing. Meaning
Yes.
the ambassador itself isn't at that Red Hat or I chose to write on behalf of the user, but it doesn't really change the model. It just says the user can use a pre-built application that does the right thing.
Yeah, sure. I mean, I think it would be beneficial for there to be community supported models for such things. I mean, be relatively simple to write, Go ambassadors on both the requester and receiver end to do that kind of
Agreed. Yeah, out of the box.
decorating and undecorating for you.
Yep, out of the box all day. But let's not miss the opportunity to let people level up who would just like to do this in their own code base if they have the skills and the means to.
Oh, absolutely.
Yep, so that's pretty much it. So right now, there are people using this pattern actually in production, which scares me, but it's a very simple pattern. People just want a token. They've already committed to Vault. They're happy with the Vault API. They use Vault in other places outside of Kubernetes. And this solution gives them the ability to use Vault in more places and decide the granularity around secrets that they want. So now the conversation is, do we in the Kubernetes community see value in something like Vault outside of this kind of initial prototype, simple use case, and go deeper?
I think I'm interested in how this solves generic secret problems. Things like, how do I store something besides a generated key cert pair, right?
So in Vault, I'll tell you, in Vault, that's kind of the initial use case. Vault, create secret, blah, right? And then you have policies that can read various secret buckets by name or pattern. So the workflow for the administrator, and I watch a couple of companies who use Vault heavily, what they do is the active managing secrets is somewhat decoupled from Kubernetes or any other platform. DBA says we're changing the database passwords, we're putting them in Vault. That's it, you know where they are. And then to consume those, it's up to you to either pull them out manually, Puppet or Chef, or have something like a controller that maps them from Vault to Kubernetes. And yeah, you're right, you have to deal with the reload problem when they change, but that's kind of the contract that Vault provides. Hey, there's a safe place to store them, an API to get them out, an audit log to see who's looking at what, and a policy mechanism to prevent various actors from accessing or creating secrets going forward.
So what we're doing at Zendesk is we're actually doing something similar with a similar controller to the certificate controller you created that populates an envdir, like basically an inverter with the secrets that a particular pod is authorized to access, and then cross-mounting that inverter into the consumer pod.
Right. So many use cases with this, but I think what I've seen the community be happy with is that Vault itself as a standalone tool is very well focused on secrets in a meaningful way, dynamic and generic secrets and custom backends if you want to do a new dynamic secret that goes out to the CIA and procures a hardware token. That's up to you. That's just Vault's world.
Yeah, I think another concrete demo, if you had another link to it here, I think would be very helpful, right? Demonstrating how that works, how I have the pod token, how I know that particular pod is allowed to access the deep database password.
So this is what I was just showing you, right? So in this demo, you saw a glimpse of it. You can extend it more, right? So if you want what you're asking, this policy here, you just add another line, right? You would say, let's say you do have some database secrets, right? You can come here, create a new line in this policy and update it at runtime, so you don't even have to change the app, and just say secrets, and then foo. So right underneath that will be generic secret bucket like we have in Kubernetes. And then you give this app the capabilities to read from it, right? List them, delete them. Well, we may not want to let them delete. We'll say you can list them. So we don't need you to update them. We just need you to be able to read and list the secrets in that bucket. And at this point, that token now has the ability to just say, hey, I want this particular secret bucket. It could be database. right? If it's a static secret, or it can be the MySQL backend. This is all in the Vault documentation, right? So it could be MySQL, and then it would be like account or something. And this
Okay,
will
and then is the request that I make for this another thing controlled by annotations?
no. So the annotation just says, what policy do you have? So right now, this is the microservices policy we have. So instead of you trying to get granular everywhere and leaking all of these
Okay.
details, you want to keep it easy for the user, right? You don't want the user doing all of that kind of thing.
Okay, so it still relies on securing who can say what particular annotation.
Right, we're back to the Kubernetes. Who can mount what secret directive?
Yeah, no, that makes sense. I was just, the demo that I just saw didn't make that obvious. Okay.
Right, yeah, so we're all trusting that if you can submit a pod, mounts either secrets or whatever, that pod is supposed to do those things. And this is why we're using an annotation here, which is the same security model that we have with the current secrets and config mask implementation today.
Sure.
I have one last question if we have time.
Yep.
So what stops can the Vault controller request a token with any policy from Vault?
Yes, there needs to be an intermediate trusted actor. Well, let me clarify that. When you create a token for the controller, you can also give it a policy that is also limited in what it can and can't do, right? So right now we're using the root token, which can do everything, God mode. But you might say, well, this is Vault, and I only want this controller to have a token that can only access maybe these 8 policies, right? So when it goes out to generate a token, it can only generate these tokens with specific policies attached to them. And if that key doesn't have that level of privilege or permissions, it will fail in its generation on token on behalf. So it's almost like this delegator pattern. It needs more. It needs the same level of permission of more than all the policies you would like to have it generate on behalf of.
Right. So if the integration point here is where does the Vault controller logic sit, then that is actually very important, right? Like if it's going to sit in the kubelet, then I need to figure out if the kubelet then has a flag that lets me access all of Vault.
That's right. Yeah, like maybe a config map or something, or a secret that the kubelet knows to reach and grab. This is what they do in Nomad today. So inside of Nomad, they have 2 ways of doing this. One, in Nomad, when you run a job, you can provide a Vault token, and then any secrets will be created based on what you can do with that token and renewed for you automatically in the background. And they do this on the Nomad agent. Or the Nomad agent itself can be given its highest level key, and then it will be able to do things based on metadata to grab secrets on behalf of the containers it's starting.
Yeah. Okay, thanks.
Awesome. Well, thank you all. That's my presentation. Hopefully it's helpful. All the code is on GitHub with these tutorials, so you can try it out, poke holes in it. I would love feedback, and maybe we can come up with some good ideas going forward.
Kelsey, I wanted to say that I really appreciate the way you structured your demo and the code. It's very, it fits the pattern quite well in Kubernetes. I did want to stress that, I think it's important to, also not forget that we have still a lot of work to go to protect the rest of the system, security wise.
Oh, agreed, totally.
Thanks for the demo. I thought it was very good.
Yeah, I can say
Thanks, Kelsey, for coming.
All right, I got to jump on another call, but I'll definitely look at the meeting notes from today if we have them.
Yep, we recorded the whole thing, I believe.
Nice. All right, I'll catch you guys later.
Peace.
All right. We are done with time. Unless there is something else specific, I will go ahead and call it here and then try to figure out what to do with the recording.
Thanks for running it, David.
Yep. Talk to you guys later.
Have a good one.